Okay, so last time we've actually had a quiz. It was the finding the capacitance of a spherical capacitor. But because we have solved that problem beforehand in the lecture, I'm not going to repeat it. Do you want me to repeat that problem? No? Okay, good. Now let me remind you what we were talking about. We are talking about capacitors, right? Let's choose a better color to write with. What was the most general definition? The definition was that if I have two pieces of conductors, if I supply a potential difference delta V to them, there will be charges stored on the capacitors, and the ratio of the charge to the voltage would be my capacitance. Okay? Good. One important example we have actually solved was if I have a parallel plate capacitor. Then the capacitance of that was always proportional to epsilon 0, which had the units of farads per meter. It's proportional to the surface area of the capacitor and inversely proportional to the distance d between the plates. Right? Now, so if I want to store more charge, we can either make A greater or D smaller. These are the two strategies we have. Now, I'm going to tell you one more thing today. I'll tell you that storing charge means I'm also storing energy. So let's actually calculate how much energy I can store in a capacitor, how much energy I store in a capacitor if I charge it with charge Q. Okay? So let's start from an uncharged capacitor. If I take dq charge from here, from one of the conductors, and move it to the other conductor, what will happen? I will actually add plus dq charge here and minus dq charge to the left one. Okay? I'm moving charge from from one conductor to the other conductor. How much work do I need to do to move dq charge from one conductor to the other conductor? I know that the work or the potential energy change to move dq from one conductor to the other conductor must be delta V times dq. But now what's delta V? So delta V, by the definition of capacitance, is Q, the total charge on one of the plates, divided by C. So now, and this should be the differential work. If I'm moving just dq of charge, it's a differential work done by moving differential charge. So what's the total work done? It's going to be integral dV, or it's going to be integral Q over C dq. And what I want to find out is, if I start from 0 and charge my capacitor all the way to Q, how much work do I need to do? And all this is going to be stored inside my capacitor, all this energy. I'm converting whatever energy I have to move the charges, okay, I'm doing some work on the system. This work is converted into potential energy, electrical potential energy in the capacitor. So what's the integral? This is the simplest, one of the simplest integrals we can see. C is a constant. So it's integral from 0 to Q dq, which is Q square over 2. So I have Q square over 2C is the energy stored in a capacitor. Or, if I remember Q is C times delta V, this is 1/2 C times delta V squared. Now, so this is the stored energy in a capacitor. As an undergraduate, one of the fun things we did in the lab was to get the biggest possible capacitor we can find in the lab, charge it to, I don't know, 1000 volts or so, and then just hand it to an unsuspecting friend. What happens when you do that? When your friend touches the terminals of the capacitor, he'll get an electric shock, right? Why all this energy will actually go through his body as a current. Of course, for the capacitors we actually find in the lab and for our voltage sources, that was just a harmless small shock. But you know, in all movies, in the movies where doctors bring someone back from a flat line, from a heart attack, those devices, they actually rely on capacitors, right? They actually have, what's the scene? The scene goes saying, you know, charge. The doctor waits for a while. What's he waiting for? He's waiting for the capacitors to be fully charged and then actually gives the current to the heart. Okay, so this is actually useful. It's getting even more useful. So here, look at this formula. It tells me that the energy stored inside energy is proportional. Okay, that's right. I mean, we've already found the formula. So this is the work, which means energy stored is 1/2 C delta V squared. So let's say I have a 5-volt battery, but I want to store 1000 joules of charge, 1000 joules of energy. What do I need? I need a capacitor with the biggest possible capacitance, right? I want to increase my capacitance so that I can store more energy for the same potential difference. Okay, so one of the proposals is to instead of batteries, which rely on chemical reactions, use supercapacitors to store charge. Okay, you make your capacitors. You have your electric car. Instead of a battery, you're going to have a big capacitor in there. You're going to charge it, and then you're going to drive your car. We'll talk about why it's not easy to do that when we talk about charging and discharging a capacitor. But nonetheless, it's a good idea to try to increase the capacitance of your capacitor. But let me ask another question. Where is this energy stored? You might say, hey, okay, it's the potential energy between charges. Now what I did is I separated charges from, I took some charge from one terminal, put it to the other terminal, so I did some work. But I'm still claiming that I can localize that energy. And where is this energy stored? So let me go back to my parallel plate capacitor. Let's say I actually gave it V volts of potential difference, and it has area A, and the distance between the plates is D. If this is my capacitor, the capacitance is epsilon 0 A over D. If I'm charging it with voltage V, the energy stored is 1/2 epsilon 0 A over D times V square. All right? Oh, okay. But I'm going to write this a little bit differently. Now, look at the system from the side. From the side, I see the following. There are minus charges here, plus charges here. And in between, I have a uniform electric field. What's the value of the electric field? Let's try to find out. Well, if the distance here is d, integral E dot dl must be the potential difference, V. But E is constant on the inside, so I'm taking E out. Integral dl is V. What's integral dl from one terminal to the other? It's the distance between these two terminals. It's d. So the electric field magnitude on the inside is V over d. Now let me come back to this formula. And this is stored energy, so maybe I shouldn't call it E, I'll call it U now. I keep changing the notation today. U is 1/2 epsilon 0 A over D times V square. I'll write this slightly differently. Epsilon 0 A times D V over D squared. How's that? I multiplied and divided by D. Okay? Nothing fancy. But what's V over D now? It's the electric field. 1/2 epsilon 0 electric field square times A times D. What's A times D? It's the volume of the region between the parallel plates, right? It's the volume that has electric field inside. Okay? So this is the volume. So here is my claim. I'm claiming that all this work went into energy which created the electric field. I'm going to claim that if you create electric field in volume electric field E in volume d omega, you store du is 1/2 epsilon 0 E square times d omega energy. Or that's better written as defining some small u, which is called energy density for the electric field is 1/2 epsilon 0 E square. So now this is a quite different formula. It tells me that electric field by itself can store energy. Remember, when I first introduced electric field, I said Right now we are doing this as some sort of mathematical convenience. Instead of writing F all the time, we say, hey, let's think that even a single charge changes something about vacuum, defines a new object, the electric field everywhere. And then if I put another charge here, it interacts with the electric field, not with the charge which is very far, which may be very far away. Now I'm actually going one step further. I'm saying, hey, electric field is very real. It can store energy. Just like if I create a massive particle, if I create an electron, by just its presence means that I have mc square amount of energy. Creating electric field in vacuum is 1/2 epsilon 0 E square energy cost. Okay. So that's an important conceptual step. It's not going to matter for us much, but we're really making the electric field a real physical object now. Okay. And it turns out, again, I'm giving a spoiler for the end of the course. We'll see that when I have light, when I have an electromagnetic wave, this is how energy is carried. Half of the energy in the in light is carried by the electric field, and the other half will be carried by the magnetic field. So energy coming from the sun to us is carried by electric field actually. Okay, half of it is carried by the electric field. But now let's solve some problems. Let's say I have two identical capacitors. And I put Q charge to one and no charge to the other. And then I'm going to close the circuit at time t equals to 0. Find the final charges on the capacitors. Calculate the initial and final energies. Okay, so what happens when I close the circuit? Will there be any charges flowing? Charges will flow. It's like touching two spheres, right? Right now, if I take the potential of the lower point to be 0, upper point here is at potential Q divided by C. But the second capacitor is uncharged. If I actually take potential here to be 0, potential on the upper conductor will be again 0. So there is a potential difference of Q over C between these two ends. So when I close the switch, this potential difference must equilibrate. What must happen? Some of the charges here must go to the other side. Good. So let's try to find the final situation. In the final situation, let's say that this is QB1 and this is Q2, and both have capacitance C. What's the condition for equilibrium? The potentials of both capacitors must be the same. So finally, Q1 divided by C must be Q2 divided by C, which means Q1 is equal to Q2. So finally, because these capacitors are equivalent, I actually have to have half of the charge in both of them. And why do I say half of the charge? Now, please follow this argument. It's going to come in handy again. Think of a surface like this. When I close the switch, can any charge come into or go out of this surface? There are no conductors passing this surface. So the total amount of charge in this surface must be conserved. Which means, if I draw the same surface again here, the total charge, here I'll have plus Q1, and here I'll have plus Q2, minus Q1, minus Q2. The total charge will be Q1 plus Q2, and that must equal the initial total charge, which was Q plus 0, which is Q. Now I know that Q1 is equal to Q2, so 2Q1 is Q. Q1 equals Q2 equals Q over 2. Not very surprising. Okay, that's pretty much what I would expect. If I have two identical capacitors, they would share the charge. But now, let's look at the energy. What's the energy in the initial situation? 1/2 Q square over C. So this is my initial energy. What's my final energy? The first capacitor has 1/2 Q1 square over C. The second capacitor has 1/2 Q2 square over C. So it's going to be 1/2 Q over 2 square over C plus 1/2 Q over 2 square over C. So it's going to be 1/4 Q square over C. Hey, which is less than my initial energy, which was 1/2 Q square over C. What happened to my energy? Any ideas? Okay, so it must be related to moving charges, right? So here is the thing. Yes. It got what? Okay, so if I had some resistance on the circuit, that's exactly what I would expect, right? When I close the circuit, there should be a current and there will be heat going on. But I did not put any resistance here. So this is a tricky problem, and your friend's guess is right. Even if I had the smallest amount of resistance, momentarily a lot of current would flow over it, and that will change my energy into heat. Even if I went ahead and did this circuit with superconductors, which I can do, it will take a while to equilibrate. Superconductors have zero resistance, but then this energy will be radiated out as electromagnetic waves. Okay? So this is actually quite surprising. At the end of the day, when I move charges over circuits, I should expect to lose some of my energy. All right? So this is radiated as heat or other kind of radiation, I should say. Okay. Now maybe I can keep thinking about the capacitor as a circuit element. What happens if I take two capacitors? C1 and C2. and connect them to a battery of V volts. I would like to find out what's the equivalent capacitance for this circuit. Now, how do I do that? Well, it's very simple. I need to calculate the total charge of the total charge stored in the system. Now, if I have delta V on the capacitor, what's the voltage on the first capacitor? It's V again, right? Second capacitor, V again. So how much charge is there on the first capacitor? Q1 is C1 times V. How about the second capacitor? C2 times V. Now, what is the total charge stored in the system? This charge must come from the battery, and if I think of the following surface, all this charge must have flown in, must have just come in from this conductor, from this wire. So what's the total amount of charge? Q is Q1 plus Q2. So I add the total stored charge when my capacitors are in parallel. So the charge here will be Q1 plus Q2. Potential is still V. So C equivalent will be Q1 plus Q2 divided by V. But what was Q1? Q1 was C1 times V. Q2 was C2 times V. Divided by V is C1 plus C2. So here is our equivalent rule for capacitors. If I have C1 and C2, this is equivalent to a single capacitor of C1 plus C2. All right? Good. How about capacitors in series? What happens if I take two capacitors, C1 and C2? Let's say they are initially uncharged. And connect them to a battery. Now, if they are uncharged, let's again think of the following surface. What's the net charge in this surface? When they are both uncharged, there is no net charge. It must be 0. When I start to charge the capacitor, I'll have plus Q1 here, minus Q1 here, Q2 plus Q2 here, minus Q2 here. But can the net charge inside this surface change? Not unless electrons are flying over the air, which we don't think they are doing. Okay? So Q1 minus Q1 plus Q2 must equal 0, which means the charges of the capacitors in series must be equal. Okay, does it make sense? Question? Okay. If the charges are equal, then I can actually calculate the voltage here. If charges are equal, let me call this Q. That's going to be my stored charge. What is the potential V1 on the first capacitor? It's going to be Q divided by C1. What's the potential across the second capacitor? V2 is Q divided by C2. So what's the total potential? It must be V1 plus V2, which is Q over C1 plus Q over C2. Or I can write this as follows: V 1 over C1 plus 1 over C2 is Q, or Q is 1 over C1 plus 1 over C2 times V, which is my equivalent capacitance. So I'll write this in a slightly easier form. 1 over C equivalent is 1 over C1 plus 1 over C2 when I have capacitors in series. Now be careful, this is just the combination laws are just the opposite of the combination laws for resistors. I've seen a lot of students mix these two up. But here, what is the physical principle I used in both cases? It's nothing fancy. I used conservation of charge. I said charges inside a region cannot change if there are no conductors coming out of that region. Okay? So when in doubt, you can actually even rederive these formulas. Any questions? Nope. Good. So let's solve an example. I'm taking a parallel plate capacitor. Let's say one side of it is L1, one side, the other side is L2. However, it's not quite aligned. Okay, so if I look at the system from the side, it's really not quite aligned, and I'll say the distance here is D1 and the distance here is D2. Okay. But I'm going to assume the following. I'm going to assume that both D1 and D2 are much, much smaller than L1 and L2. Furthermore, the alignment is almost perfect. It's only a small mismatch. All right? Now, why am I assuming this? Because it turns out all the formulas I'm using to calculate capacitance for these parallel plate capacitors assume you have infinite conductors, right? I've been implicitly using electric field is sigma over 2 epsilon 0 for an infinite plane. And I'm using it for non-infinite plates. The only way my formulas are going to be correct is if the conductors are so close to each other that within the region, within this capacitor, I can regard each one of the plates as infinite plates. Right? So that's an approximation. Now, how am I going to solve this? And here's my idea. How would you solve? So I'm asking what's the capacitance of this object. How would you solve the following problem? If I had one capacitor of area A1 and distance D1, another capacitor of area A2 and distance D2. And if I actually connected these in parallel, what would be the equivalent capacitance? Well, I would find C1 and C2. It would be C1 plus C2. So it would be epsilon 0 A1 over D1 plus epsilon 0 A2 over D2. Right? What if I had 3 capacitors of different distance? They'll still be connected in parallel. I can actually calculate the capacitance of each one of them and sum. So my idea will be to do that. So here is my unaligned capacitor. I will say this is actually made up of small capacitors. If the distance here is x and the thickness in one direction is dx, I'm going to find dc of this capacitor. Okay. So this is going to be infinitely many small capacitors in parallel. Does that make sense? Does everyone understand the geometry? Yes.
Why is it why have you drawn the first line as slant? Why is it not straight?
So that's how you actually okay. Let's say you're an engineer, you're trying to build a capacitor, but somehow you're not the best engineer in the world. Okay, so you could not align these plates. So the distance on one side is d1, the other side is d2. Okay, so the question is, what's the capacitance of the system? Right, that's the geometry. Now I'm saying we don't have to make big calculations. We should think of the system as infinitely many parallel plate capacitors in parallel. Right. So essentially I'm saying, let's take a distance x from here. Here, this is going to be my lower plate, and correspondingly I will have an upper plate. So there will be a small capacitor DC of capacitance DC there. So can you tell me what's the surface area of this small capacitor? I think it's best seen here. One side is dx, the other side is L1. So dA must be L1 times dx. What's the distance d? Or let's call it y here, okay? As a function of x. Distance between the plates for this small capacitor. Well, so the distance on one side was d1, the distance on the other side was d2. So I'm claiming y of x is a linear function of x. When x is equal to 0, it's d1. When x is equal to the whole length is L2, when x is equal to L2, what must it be? It must be d2. So x is L2, x over L2 times d2 minus d1. Did I do this super fast? I just said y of x equals 0 is d1, and y of x equals L2 is D2. It's a linear function. If I fit 2 points, I found the function itself. Or, if you prefer, you could say, let me take a triangle here. Okay. The distance here is D2 minus D1. So the distance here must be D2 minus D1 times x divided by L2. So the full distance y of x would be D1 plus D2 minus D1 times x over L2. I think it's the same formula. Okay? How many of you are following me? Those of you who are not following me, please can you raise your hand? If you're not following me, you cannot raise your hand, right? So, okay. Please let me go over this argument once more. I had a slanted capacitor. The capacitor is not quite aligned. What am I doing? I'm splitting it into infinitely many small capacitors. And right now, I'm trying to find the capacitance of a single one of those capacitors. For that, what do I need? I need the area of this small capacitor and the distance. I found both, which means the small capacitance is epsilon 0 dA over y of x. So it's going to be epsilon 0. dA was L1 times dx, and y of x is d1 plus d2 minus d1 over L2 times x. Now, what's the total capacitance? I need to integrate all these small capacitances. What are, let me write everything down, L1, L2, D1, L2 plus D2 minus D1 times x times dx. What are the limits of my integration? I must start from x equals 0 and go all the way to L2. From 0 to L2. Let's check epsilon 0, L1, L2 are nice and easy variables. They are constants. I took them out. How am I going to evaluate this integral? By a simple substitution, the way we evaluate all our integrals. I'm going to call u as d2 minus d1 times x plus d1 L2. So this is going to be epsilon 0 L1 L2 times. What's du? du is d2 minus d1 dx. What's the lower limit when I put x equals to 0? I start from d1 L2. When I put x equals L2, I find d2 L2. Some phone is going off. Okay. Now, I have 1 over u, and dx is du over d2 minus d1. All right? So, epsilon 0, L1, L2 divided by d2 minus d1. Right? What's the integral? 1 over u du. Come on. ln, right? So this is going to be capacitance is epsilon 0, L1, L2, d2 minus d1, ln d2 L2 divided by d1. L2 is cancelled. Epsilon 0, L1, L2, 2 minus d1, ln d2 divided by d1. All right? Now it's kind of not super easy to check if we get the correct limit when d1 goes to d2. When d1 goes to d2, what should I have? I should have epsilon 0 L1 times L2 divided by d, or d1, right? But now I have a result which seems to be blowing up d2 minus d1. But ln d2 over d1 also becomes 0 when d2 is equal to d1. So actually this is the correct answer. Okay, so and dimensionally it's epsilon area over distance, so it should be okay. Okay? Any questions? Okay, so let's take a 10-minute break, and when we come back we'll talk about dielectrics.